One shared gateway is great until one team burns the budget for everyone else. I'll use LiteLLM Proxy to cap spend by team, route traffic cleanly, and keep fallbacks under control. This is the setup you'll be able to run after this, which sets team and key limits and routes a request across providers within caps.
I'm Professor Pi, teaching AI engineering and LLM systems with simple Python.
Shared proxies feel convenient, but convenience becomes chaos when one project runs up cost and knocks everyone offline. Teams need predictable limits. Engineers need routing that respects those limits and still finds a healthy provider. LiteLLM Proxy gives us admin endpoints, team-scoped keys, and routing aliases so we can enforce limits and shape traffic without changing client code. At a high level, we want three things. 1. Verify the gateway is reachable. 2. Create and inspect team budgets. 3. Create keys and route calls through a named alias that balances providers. Success is a request that uses the right team budget and lands on an acceptable provider. We will build a concise flow you can run locally. It will test connectivity, provision 2 teams, pick the highest budget team, mint a key for that team, and then define a routing alias to balance 2 providers for a chat request. That makes later scaling and monitoring straightforward. Now we will check connectivity to the running proxy. This snippet pings the LiteLLM Proxy and lists available models. It creates a request session, so subsequent calls reuse the same TCP connection and headers. The variable base URL targets a locally running proxy, and the GET call hits the OpenAI-compatible v1 models endpoint. The response R is parsed as JSON into data, and the list comprehension extracts each model ID into models. Finally, the print shows whether the proxy responded successfully and how many models are available. If you increase the timeout, transient slow starts are less likely to be flagged as failures. This quick connectivity test matters because it confirms the gateway is reachable before adding budgets or routing rules. Next, we will create team budgets, so each group gets a daily cap. This example creates 2 LiteLLM Proxy teams with daily budget caps. The list teams holds concise dictionaries defining a team ID, a budget in USD, and a reset period. The comprehension posts each definition to the /v1 manage teams admin endpoint using the shared session, returning response objects into res. The added variable counts how many creations succeeded by checking each status code. The final print reports how many teams were provisioned and echoes the last HTTP status to verify the operation. If you raise a budget value, that team can spend more before enforcement. If you lower it, traffic from that team will be constrained sooner. This confirms budgets are now enforced server-side. Now we will list the teams and find which one has the most headroom. This code fetches teams from LiteLLM Proxy and ranks them by budget. It calls the v1 manage teams endpoint to retrieve the current team list as JSON, then reads the data array into the variable teams. The max function selects the dictionary with the largest budget field, guarding for empty results with a fallback to an empty dictionary. The print displays the highest budget team and its available limit, which is helpful when deciding where to route heavier queries. If you update team budgets via the admin API, rerunning this selection will immediately reflect the new ordering. The printed winner highlights where you have the most headroom for spend right now. Next, we will mint a key tied to a team and send a small chat request to exercise budgeting. This snippet provisions a team-scoped API key and sends a chat request. The first post to /v1 manage keys creates a key bound to the analytics team with a budget, and the returned key is stored in K. The second post targets SV1 chat completions, using the authorization header with that key, so the proxy can meter spend against the correct team. The payload includes a small messages array and a user string for end-user attribution and traceability. A short timeout keeps the client snappy under failure. The printed HTTP status and request ID confirm a successful budget-enforced call you can trace in LiteLLM logs and spend views. Now we will define a routing alias that balances traffic and then call it. This example defines a routing alias and sends a request through it. The dictionary route declares chat balanced with 2 candidate providers and waits, then posts it to LiteLLM Proxies /v1/manage/routing admin endpoint. The next call hits v1 chat completions using the model name chat balanced and the previously created team key KA. The proxy selects a backing provider using the configured weights and returns the chosen model in the response JSON. Increasing the first weight biases selection toward OpenAI. Decreasing it shifts more traffic to Azure. The printed selected model confirms which provider actually served the request, so you can verify routing behavior before scaling traffic. In a production setup, you would map these same steps to your team directory and monitoring dashboards, so budget hits surface as alerts rather than surprises. Linking the team ID to your billing and incident pipelines closes the loop between policy and operations. Recap: it enforces per team spend and routes requests through named aliases so you can shape provider usage. Use this when multiple projects share a single gateway and you need predictable budgets and graceful fallbacks. One caveat: administrative endpoints must be protected and audited, or budget rules can be misconfigured. Next step: tune the routing weights to shift traffic between providers and measure latency or cost impact under realistic load. Start by nudging one weight up or down, and observe which provider serves more traffic and how spend moves. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.